All right, welcome back. So today we're going to carry on our discussion of a microscopic formulation of gauge theory based on the real space lattice. And in contrast to the usual discussion of gauge theory on the lattice, we're not going to do it in Euclidean Wick rotated lattices, but instead we're going to build a Hamiltonian microscopic theory for gauge theory. And in the last lecture, I already introduced to you the basic ingredients of formulating a microscopic gauge theory, so one that's at the scale of a cutoff. If you remember from the previous lecture, the degrees of freedom, the classical degrees of freedom of a microscopic lattice gauge theory are a selection of 2 by 2 matrices, call them U, one per link. Right? These things are called links here in this lattice. And we have a U for each link in this lattice. And what's U? U is a parallel transporter. And for all the discussions we're going to have in this course, we're going to focus on the gauge group SU2, not on SUN, but there's no difficulty in generalizing everything I say to SU3, 10, 1,000, whatever SU you like, or indeed whatever Lie group you like. So this U here is meant to represent, it is the parallel transporter for a degree of freedom to be parallel transported along this link here. And these links are of length A, and that's this lattice spacing, and you want that to be quite small. That is, in fact, our cutoff. So A is 1 on Kc, if you like, the cutoff for our theory. So these U's are non-local objects, as I stressed when we introduced gauge theory at the beginning. U depends on 2 parameters. In fact, it depends on the path that you take, these parallel transport operations. It not only depends on the endpoints, but like, do you go in a straight line between these endpoints, or do you go in a curvy path, and so on. So these U's are meant to represent parallel transport along a straight line along this link here. Let's call this link E. And if you have 4 space-time dimensions, then you will have a 4-dimensional lattice, and you need a U for each link in this 4-dimensional lattice. Right? Easy, right? But that's the classical. This is the classical story. And while that is actually an interesting story, the classical theory is not entirely trivial, not by a long way actually, so there's a lot to learn even classically. We're not going to be so interested in the classical side because we want to build quantum field theories, we don't want to build classical fields. We're a bit more ambitious. And so we want to quantize this story. And if you think that the fundamental classical degrees of freedom are 2 by 2 matrices, 1 per link, then your experience with ordinary quantum mechanics would tell you that, well, okay, the way to quantize this, the most naivest way, is to take wave functions. I should say that the configuration space, the classical configuration space for a lattice gauge theory is given by the following. So classical configuration space for this lattice gauge theory is the Cartesian product of SU2 over all the links. You've completely specified the classical configuration of this lattice gauge theory if you've given a 2 by 2 unitary determinant 1 matrix per link in the lattice for every link. And SU2 in turn, it's very special to SU2, but very useful, is in turn diffeomorphic to this 3-sphere. So it's enough to specify 3 numbers, or 4 numbers of length 1, 1 per link in this lattice here. So that's classical configuration space. I don't know, let's call it calligraphic C. And, well, to quantize a theory that's got a classical configuration space, like the simplest, dumbest thing you could do, the thing that you would learn in Quantum Mechanics 101 is just take as your configurations now for the kinematical Hilbert space to be the space of all wave functions on this classical configuration space. And what does that mean? Well, psi as a ket lives in some Hilbert space, and we have to describe what is this Hilbert space. This Hilbert space is a tensor product over all the links of some other Hilbert space, HE, that's the Hilbert space per link. And I told you what that was in the previous lecture. It's a space of square integrable functions on SU2. And that, like the picture that I have in mind when I write down L2 of SU2, because SU2 is diffeomorphic to the 3-sphere, I always think that a wave function on SU2 is really just like a wave function on a sphere. So I always draw a sphere to represent the classical configuration space. I know that's S2 and not S3, but you know, have you ever tried to draw S3? It's not trivial. So this is meant, this 2D projection of S2 is meant to represent S3. And the space of wave functions on SU2 is basically the same as the space of wave functions on S3. So it's just like a complex number per point on the sphere. And then you can see where spherical harmonics and angular momentum is going to start to enter this picture. Yep. We now understand the kinematical Hilbert space for Hamiltonian Lattice Gauge Theory. It's no more complicated than that. So let's try and understand this little space first. So I've given you a definition of the kinematical Hilbert space. It's written right there. Really, the naivest one basically works. But in order to understand capital H, we're going to have to understand L2 of SU2. What kind of space is this? Well, the first question we can ask is it finite dimensional or infinite dimensional? And the answer is it's actually infinite dimensional as a Hilbert space. There's an arbitrarily large number of orthogonal wave functions on the sphere. So the spherical harmonics just go forever. And we want to understand the structure of this Hilbert space a bit. And the way to do that is we're going to need to represent some unitary processes on the space in order to say anything more. At the moment, this space is just infinite dimensional separable Hilbert space. That's all we know at this point. But of course, we have some more structure. And the first structure we're going to discuss is the action of SU2 on this space. And I introduced that in the last lecture. So SU2 acts in a canonical way, right? Standard way on this space. And it acts in non-canonical ways, but yeah. We're not going to need non-canonical actions. So how does it act on there? Well, I introduced these two operators in the previous lecture. Left and right multiplication by some SU2 unitary. So this is a unitary action. LU is unitary, RU is unitary, and in fact these guys commute with each other. So this forms a representation. And I believe the way I set them up is that it really does form a representation. Actually, I think I didn't. Oh, no, I did. Yeah. It was set up, these operators were set up so that they give actual representations of SU2. So we also have that LUV is the same as LU times LV. Now, if you've got a representation of a group on a space, then you can use representation theory to decompose this space into irreducible representations of the group. So I'm just going to quote a theorem at you rather than go into the details of the representation theory of SU2. You by now have seen the representation theory of SU2 enough times to be comfortable with the basics of it. And all I'll do is quote the result that we need for this lecture. So the theorem we need to understand how this infinite dimensional Hilbert space breaks up as a direct sum over irreducible representations of SU2 is a theorem known as the Peter-Weil theorem. That's a big theorem with many pieces. We're not going to need all these pieces in this lecture. It's like 4 data points inside the Peter-Weil theorem. So the Peter-Weil theorem is this big heavy theorem about the structure of square integrable functions on a Lie group. We're only going to need a very specific consequences of this theorem. And the specific consequences that we'll need is that this particular Hilbert space here, the Hilbert space for one link, breaks up as a direct sum over the irreducible representations of SU2 in a very particular way. It's not just got to get the star in the right place and then we're good. Yep, there we are. So I'll explain what all these symbols mean. have to orient myself slightly. So L2 of SU2, that's some Hilbert space. SU2 acts on it in two ways, from the left, from the right, independently. You know that any space where a group acts on it is going to break up into a direct sum of smaller spaces on which the group acts irreducibly. And how it breaks up depends on the space and the action. So it could be very complicated. It could be multiplicity. There could be large numbers of repeated irreps in there. However, for L2 of SU2 or L2 of any Lie group, it turns out to be super nice the way this space breaks up into a direct sum. It breaks into a direct sum over the fundamental irreducible representation of spin L, or angular momentum L, tensored with its dual. This just means dual, right? And at this stage, the dual is isomorphic to the VL itself. And it's a direct sum over all the irreps counted once. There's no multiplicity. So it's super nice how it breaks up as a direct sum. And this half Z plus, those are the labels for the irreps of SU2. You know that the irreps of SU2 are labeled by half integers. This is the spin, 0, a half, 1, 3 halves, 2, etc., etc. And these representations are, these vector spaces VL are isomorphic, right? They're not very complicated vector spaces. They're just the complex numbers to the power 2L plus 1. So there's your basic reminder of SU2 representation theory right there. And on those vector spaces, these L's act in a specific way. And I can remind you of those. That's the bit that gets kind of annoying, that you probably never went beyond spin 1. But it turns out for discussing lattice gauge theory, you will need to know about the higher spin representations of SU2. It's just the nature of the game. So let me tell you the coolest thing I know about Lie algebra Lie group representation theory that I have yet to find in any textbook. So we've got these spaces VL, and SU2 acts on VL in a specific way. They give you a representation of SU2. So and to fully understand this representation, you're really going to need to know this matrix here. What is this matrix? Now, you can pick up your quantum mechanics textbook or your Lie algebra Lie group textbook and look up how to build these matrices, and it's a monumental pain. Right, there's raising operators, there's lowering operators, there's Casimirs, there's highest weight vectors, and just to get this 3 by 3 matrix in the case that L is 1 seems like an unbelievable amount of hard work, and there's these square roots of things, and it's a real mess, right? So I'm going to show you a quick way today to get these matrices for Lie groups. This is the awesomest trick that's not in your Lie group textbook. And what do you need? So what you need. To understand this trick. You'll need to understand the matrix elements of the spin half representation of SU2. You'll need to know A, B, C, D. You need to know the fundamental representation of SU2, but I think you know that, right? The spin 1/2 representation of SU2 is none other than just put in the four matrix elements of SU2. So you need to know the spin half representation, otherwise known as the fundamental representation. And you will need to know about tensor products. And that's it. Once you know these two things, I can get you any representation you like. Super quick, super easy, and extremely explicit. You will not need raising and lowering operators. You will not need to exponentiate these matrices, blah, blah, blah. No. With this 2 bits of information here, I'm going to show you how to get the matrix elements of this matrix in any spin. And the way we're going to do it is as follows. So it's an algorithm. To get the spin L representation, we're going to take the tensor product of VL, otherwise known as C2, right? 2 by 2, two-dimensional vector space. That's the vector space that affords the fundamental representation of SU2. And the number of times you need to do this is equal to the spin of the representation you want to find. Oh, whoops. Sorry, that's always a half. So if you want the spin L rep, VL, and you want pi of L, how this matrix acts on that vector space there, then what we're going to do is we're going to find this space inside the tensor product of spin 1/2 spaces. And this space lives in there as long as L is equal to, there's a missing number here, n, as long as L equals n divided by 2. So we need that n equals 2L. All right, that's easy, right? We know what this vector space is. If you're a quantum computer fan, that's the space of n qubits. Now, let's build a cool basis for a subspace. So we're going to build VL as a subspace of this space there. So we're going to take too much. VL, we know how big VL is, right? It's 2L plus 1 dimensional. And we know the dimension of this vector space here is super huge, c to the 2 to the n. So, well, this seems like a pretty wasteful way to construct this vector space. But you'll see that we're going to throw away almost all of this vector space in order to construct our VL. Okay. So now we build a set of orthonormal vectors for this that live in this big space here. And they're going to be really easy to remember. And that's the beauty of this construction. If you know about Young tableau and all that sort of stuff, I'm just using, this is a baby version of Young tableau. But of course, why learn all that Young tableau stuff if all you need is the baby version? So I'm going to specifically throw away all Young diagrams and all that sort of stuff and just write out as simply as possible a bunch of matrix elements that will give us these pi L's. It's specific to SU2. You can generalize it to SU3, but at some point you'll realize that the Young-Tableau approach is in fact more efficient. But so here's the basis. I'm going to label the two basis vectors of C2 as 0 and 1. Right? They're qubits. Why not call them qubits? Well, yeah. Okay. Okay, that's a vector, right? It's the vector with all ones. Easy. This vector here, oops, n, is the vector of all ones but with a 0. And you just take the superposition of all places where that 0 could be. I'm going to call that vector w of n minus 1 over 2. W of n over 2 minus 1. And the way you build these vectors lower down is you have 1 over n choose k, and you just write out all the places where those zeros can be. There's k zeros and the rest ones, plus all permutations thereof. And then you go down and you end up with this vector here, w of minus n over 2, and that's with all zeros. So there are n plus 1 of these vectors, if I've done this correctly. So what's the data you need to keep in your head so far? What do you need to remember to build these representations? Well, you need to know this fundamental spin 1/2 representation. I assume you know that, right? You know that a 2 by 2 unitary matrix with determinant 1 has matrix elements A, B, C, D, obeying some quadratic relations. And you also need to remember these n plus 1 vectors there. But I claim that that's not very much surface area, right? You can remember how to construct these W vectors. You know it's got something to do with permutations and zeros and ones. So as long as you remember that, you'll be able to work out these normalizations there without thinking too hard. Well, that's it. That's all you need. We've already built the representations. I'm going to give you the matrix elements now. I mean, this is all done without proof, but if you're willing to take things on faith just because you want a representation now, this is super useful. So then, let's work out the matrix elements of pi L of u. This is the hard job that we have, right? Or is it hard? Actually, maybe it's easy, and it is indeed easy. So here it is. J these matrix elements, these 2L plus 1 times 2L plus 1 complex numbers, are none other than, oops, sorry, are none other than these numbers here. That's the matrix elements for the spin L representation of SU2. Pretty cool. It's a little bit complicated to calculate these numbers, as it must be, right? It's not trivial to calculate these numbers. But it's a very efficient way to remember them. And it works pretty well for low spin representations as well. I mean, at some point, this is not very efficient, right? When n is 1,000 or something, then you don't want to be working with the Hilbert space of 1,000 qubits. It's too big. That's when you start to see the value in learning about addition of angular momentum and Clebsch-Gordon coefficients. But for low spins, and that's usually all you want, this is an extremely rapid way to build up these representations where you don't have to worry about raising, lowering operators, highest weight vectors, blah, blah, blah. This is exactly the matrix elements here. And you can see that it reproduces all the representations you know. So for spin 0, I didn't write out the case for spin 0, but you can imagine that that's C1, right, the one-dimensional vector space. We know that the matrix elements, it's just always 1 for spin 0. It's a one-dimensional vector space. What about spin 1/2? Well, if you work out the matrix elements according to this recipe here, you're going to get 2 vectors, namely 0 and 1, right? And the matrix elements are none other than the matrix elements of the unitary itself. And let's do something non-trivial. This is a calculation that nobody really likes to do. Spin 1, right? Usually that's a real pain if you want to work out the matrix elements of the spin 1 representation of SU2. That's what made me try and cook up this method in the first place, because I got so annoyed at all this raising and lowering nonsense. So let's do spin 1 in some detail. So we got W1, we got W0, and we've got W minus 1. Three vectors. Let's work out the matrix elements. It's a 3 by 3 matrix. We know that pi 1 of u is going to be a 3 by 3 matrix because the dimension of that representation is 2 times L plus 1, so it's 3. Let's start working out some matrix elements, all right? Let's work out the minus 1, or yeah, let's look at the 1, 1 matrix element of this unitary here. How hard can this be? And the answer is not very hard at all. You just use this prescription. Done. There's only one really complicated one, right? Zero, 0. So here there's a couple of terms to worry about. There's in fact 4. What are these numbers? Let's work them out. So we need the one entry of u, that's A, according to the parametrization I gave up there. It's A. Times by the 0, 0, which is B, right? Oh, wait, on C. Okay, I realize that I've done this slightly oddly. That's how I'm parameterizing the matrix elements. Okay, it's not ideal, but you could, if you don't like that convention, then you can just change it. So then we want the 0, 1 entry of u. The 0, 1 entry of u is C, And we want the 1, 0 entry of u, which is b. And we want exactly the same thing again, right? Just 1, 0 times y 0, 1. It's easy to work out. It's just the same thing again, cb. So 2 times cb plus the 0, 0, which is... Oh, yeah, that's wrong, right? 0, 1, 0, 1. Yeah, right, that was wrong. And then we want the 0, 1 entry, and that is, well, AD again, right? And so we're done. We've got AD plus BC. So if you can now use this recipe and you'll build up a 3 by 3 matrix for this pi 1 of u. We know 2 entries already, right? A squared and AD plus BC. It's not sort of surprising that I'm going to put a c squared in there. And what else do we need? Well, there's a bunch of other elements to fill in. Won't take you too long now that you see the trick. And that is how you build a spin L representation of SU2. It is pretty efficient for small numbers, for small L's. But of course, as L gets bigger, you don't want to be constructing this huge vector space in a computer. But you can, I mean, by thinking about it and using this representation here, you can make it a bit more efficient. But in the end, you'll want to transition to more sophisticated methods if you want large spin representations. But this is just fantastic for the small cases that we care about. So, knowing the Peter-Weyl theorem, knowing this trick here, we can very quickly work out how L2 of SU2 decomposes and how SU2 acts on it. So that's what the Peter-Weyl theorem tells us, that the Hilbert space of square integrable functions on SU2 is a direct sum of these tensor products here. And we also learn how SU2 acts on this space, and it acts as a direct sum of L is a half Z plus pi L U tensor the identity, for example. And we now know the matrix elements of these matrices here. So we have a fairly good working understanding now of this Hilbert space. It's just this infinite dimensional Hilbert space here, and how these operators act, namely via these unitary operators here. And I like to say that this is only just barely infinite, this space. So it is infinite dimensional, but for a large, if you truncate the angular momentum, if you say there's no spin above 10 million, then it's a finite dimensional Hilbert space. And that makes physical sense, as we'll see, wanting to truncate this for some finite angular momentum. All right, what else do we need? Yeah.
How exactly do you mean the last line on the board?
How do I mean the last line on the board?
Is isomorphic
Oh, what on earth does this mean? Yeah, right. It means this.
I thought LU is the operator.
LU is an operator, yes. LU acts from, goes from L2 of SU2 to L2 of SU2. And this thing here, that's a matrix, that's an operator. Yeah. So this is a matrix, this is an operator, it's all an operator.
Sorry.
Yep.
Question to this cutoff. You mentioned like we can cut off this theory by 10 million spin. How do we know that these LUs converge to some way we cut off these?
Okay, so the question is, how do we know if we cut off at some large L that these operators would converge to these operators here? Well, that's part of the Peter-Weil theorem, so that's, yeah. You know, I don't have a simple answer to that, but on any state with a low enough angular momentum, if you cut it off, you'll see that it's immediately acting the same. So if I have some input state, that depends, that has angular momentum 10, and I cut it off at 1 million, then this operator, this cutoff operator already acts correctly, as long as the cutoff is bigger than the state that you're acting on. So it converges very rapidly indeed in matrix elements. Okay, there's a bit more to the Peter-Weil theorem that we will need actually. And that is that these matrix elements here, we're going to interpret these matrix elements here themselves as functions on SU2. This is probably the hardest sort of conceptual jump in all of this. So pi L, the j-kth matrix element of pi L, is a function of the matrix that you put in there, right? So this means it's a function from SU2 to the complex numbers. So it's itself a function. And, you know, e.g., right, L is a half, then pi L dot, let's call it, you know, 1, 1 in the notation up there. That's none other than that function there. A is the function on SU2 that takes the 1, 1 entry of the matrix U. So it's a legitimate member of L2 of SU2 itself. So we can give it a name. What name did I use? T. All right. So what does it say? It says that this matrix element here, the j-kth matrix element of the spin L representation, which is a number, that's an element of L2 of SU2, right? If you take out its argument, the function, the matrix, then you can think of it as a function from SU2 to the complex numbers. And it's square integrable because the manifold SU2 is compact, so it's not going to diverge because it's a polynomial in the entries of the matrix U. So if you put the argument in U, then you get this. is. And this next part of the Peter-Weyl theorem that we will also need is that this set of functions here forms a basis for L2 of SU2. That's probably the most important part of the whole story. Very, very important observation. This forms a basis, so as L runs from 0, 0, a half, 1, 3 halves, and J, K run between L and minus L. Okay, it's a list of functions. They're all square integrable functions, and they form a basis for L2 of SU2. And that's the most important information we're going to need about L2 of SU2, because it tells us that every state, every function from the Lie group to the complex numbers is expressible as a linear combination of these states here, these wave functions. Yeah, question? Forms and ortho. Oh gosh, yeah. L2 of SU2. So what does orthogonal basis means? It means everything can be expressed as a linear combination of them. So we're going to use a little notation. I'll explain it in 1 second. Because we're going to put kets around our wave functions to think of them as vectors, right? This is a wave function. So as an element of a vector space, I can put a ket around it. Well, that's the ket you would normally write around a wave function, but I prefer this notation there. And it's not far wrong as a notation. All this discussion of the Peter-Weyl theorem so far has been a way to give us a nice orthonormal basis for L2 of SU2. And it's nice because it's a countable basis, right? Whereas before, it wasn't clear what was a nice basis to use for this infinite dimensional Hilbert space. Now we have a nice orthogonal basis there. The normalization, it's orthogonal, not orthonormal, because these things aren't normalized. We'll normalize them in 1 second. Yeah, in fact, I'll normalize them right now. Now they're orthonormal. These kets down here are orthonormal basis. And the normalization comes from integrating over the unitary group. So there's an inner product. This is Haar measure. This is the unique left and right invariant measure on the unitary group. And this inner product gives us a way to tell if these elements here are orthogonal or not, what we learn is this. This is also the Peter-Weyl theorem, if you like, but if you do that integral over the unitary group of these matrix elements, you'll get the number 1 on 2L plus 1 with a bunch of delta functions like that. So that's where that normalization comes from there. And do I have a quick argument for that? No, nothing that I'm going to tell you in today's lecture how to do this integral. There are some tricks you can use with this representation I showed you. So if you integrate over the unitary group a tensor product of u's, then you get special projections. So I'll give you a hint at how this is derived. So if you have something like U tensor U dagger, and you integrate over the unitary group, that's going to give you some, it's going to be proportional to the identity plus the swap operation. So that's a little fact about, and you can set these numbers by taking the trace of both sides. So that's a little fact about, or the determinant is easier, I suppose. Yeah, the trace. That's a little fact about integrals over SU2 that you can use to derive eventually that result there. So I'm not going to prove that. That's an awesome exercise that I will not deny you the pleasure of. Good. So we have a basis for L2 of SU2. We can express any ket that we like in terms of that basis. And so now we have a basis for the full Hilbert space. Blah, 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 right? It's not very helpful at this stage, but it is a basis. You just take the tensor products of these things over all the links in the lattice. All right, I need one more, well, I guess two more operators, and then we can define our microscopic model. That's about right. All right, to define our model, the thing that gives dynamics to this theory, we're going to need some more observables on this Hilbert space. So far we just talked Hilbert space, and one operator, namely LU and RU. LU and RU are unitary, so they're not very good observables, right? Unitaries are not themselves observables in quantum mechanics. We're going to use them to build some observables, and I'm also going to introduce some other observables. So first, let's remember that if U is an element of SU2, then U is the exponential of some element of the Lie algebra of SU2. And I want to get the numbers exactly right. So it's going to be am I using J's or alphas? J's and K's. Okay. minus. So every 2 by 2 unitary matrix with determinant 1 can be written as the exponential of the sum of the 3 Pauli operators with some coefficient Cj here. Cj are real numbers in this case. That's a fact, right? And you can prove that fact to yourself by just taking the logarithm of any 2 by 2 unitary matrix with determinant 1. And you'll see that it must be an imaginary number times by a Hermitian operator, which you can express in terms of the Pauli. So that's a fact. And we're going to use this fact to design a special observable, or in fact 3 special observables, for our Hilbert space L2 of SU2. So these tau's there are not the Pauli operators. They're the Pauli operators multiplied by I and divided by 2, I think. It's just a normalization issue, but one to be aware of. Okay, let's design our first set of observables. The way we do it is we remember that we can get the Pauli operators by differentiation. So if you do d ds of e to the s tj, and then you evaluate that at s is naught, then what do you get? Well, you get tj, right? That's easy. Because that forms a 1-parameter subgroup. And then if you differentiate, everything commutes, and so you can differentiate and you get, there it is, super. So our observables that we're going to build, we're going to call them left angular momentum observables. Or kinetic energy, momentum, really angular momentum observables, is we do exactly this, but instead of using this fundamental representation of SU2, we're going to use this LU representation of SU2. So we take this nice unitary operator here, left multiplied by that unitary, differentiate it, and evaluate it at s equals 0, and that's going to give us factors of I times by a Hermitian operator. That's okay, we'll do it that way. It's some unitary operator, you differentiate it to get some anti-Hermitian operator times by a unitary, you evaluate it s equals naught, it's going to define for you this anti-Hermitian operator there. Anti. So it's just a factor of I away from being a Hermitian operator. So if you like, this is analogous to I times the momentum operator in normal Schrödinger mechanics. And we also have the right angular momentum observables defined exactly the same way, but using R. Turns out we'll just need the left ones. Okay, those are momentum type observables. We're going to need, to get something non-trivial, we're going to need position type observables. There's 4 of them, and when you act them on a position eigenstate, it just gives you the spin 1/2 representation like this. The jkth matrix element of the spin 1/2 representation of U. So remember, this is a sort of an eigen position eigenket that I defined in the previous lecture. So that's just a ket put around an SU2 matrix. And this is an operator, is a Hermitian operator. No, it's not Hermitian. It's just an operator. And it goes from L2 of 2 to SU2, L2 of SU2 to L2 of SU2. And although you might not sort of see it from that expression there, just think of expanding psi as a wave function. And then acting with this operator. And then you see that the action of this position operator is to multiply the wave function by none other than t of a half. So the position operator acts like the position operator does in normal Schrödinger mechanics. The position operator takes a wave function, u is thus analogous to position, and multiplies it by position. Yo, question?
Maybe a stupid question, but why did you circle the psi due to include the pi on half of u, jk, dt1?
Oh gosh, yeah, right. So the question is, why did I circle both things? Well, I'll save that by just saying that the circled stuff is equal to that. All right. Now we've got some operators. We have position, operators analogous to momentum and operators analogous to position. And now we're going to build a Hamiltonian, which is like kinetic energy plus potential energy. That's our objective. There's one more thing we have to build before we do that. We're going to have to build a thing called a plaquette operator. So that's going to be an operator. Also goes from no longer SU2, but SU2 4 times. So how do we build this operator? This is the most complicated operator in the whole story. So if we go back to our original lattice, and we label these links as E1, E2, E3, and E4. There's 4 links in this plaquette. This is a plaquette here. And there's 4 links involved in that plaquette. And then what we're going to form is we're going to first form the following operator. It's going to be uj1k1 uk tensor uk1 yeah, j's and k's, yeah, k1 k2 tensor uk2 k3 tensor dagger u hat dagger k3 k4. Sum them over k1, k2, and k3. We're going to form this funny operator here. And these u's, this u is the u observable for E1. That's the u observable for E2. This is for E3, and that's the u observable for E4. I'm going to form this funny operator here and sum over these 3 k's. So if you think about taking a walk around this plaquette, as long as the arrow is in the direction of our walk, we tensor on u's, but if the arrow is in the wrong direction, we dagger them. And so we end up here. So we do a little walk, and we form that operator there. I don't know what to call this operator. Let's call it, I don't know, M plaquette hat comma JK, J1 K4. That's the 2 variables that aren't yet summed over. And the actual observable, we're going to denote that we're going to need for our microscopic model. I'm going to denote with trace of U hat plaquette. This is an abusive notation. It's not quite right. It's going to be defined to be the sum of over J over K4, this M operator. So it looks like a trace, right? If you think of these as matrices, these as matrix elements, you can see this looks kind of like matrix times matrix times matrix, and then we want to sum K4 equals to J1. That looks kind of like a trace here. So this is an operator. It's not a number, it's an operator. And that operator acts on L2 of SU2, tensor L2 of SU2, tensor L2 of SU2, tensor L2 of SU2. It acts on these 4 Hilbert spaces there. And that's more or less it. That's what we need to define now our microscopic model for this lattice theory. So let's now write down our microscopic model. It's called the Kogut-Susskind Hamiltonian in honor of its inventors. And it's defined as follows. We take the sum over all the links . Now I've got to get the constants right. Minus G. Is 2. Yeah. So we have these left angular momentum operators that act on link E, and I take them squared. Now they're anti-Hermitian, which means when I square them, I get negative a Hermitian operator. So that's okay, that's actually Hermitian. And then we're going to sum over the plaquettes. These these plaquette terms plus the Hermitian conjugates. Yeah, I believe that's correct.
Sorry?
Yeah?
You assume some periodic boundary conditions, or what happens at the...
Well, yeah, I've been a bit vague about what happens at the ends of the lattice. So the question is, do I assume periodic boundary conditions? You can assume whatever boundary conditions you like. This works for a finite lattice, it works for an infinite lattice. If you have like open boundary conditions, these plaquettes are not so well defined, you can just choose not to impose them at the boundaries. So if you have a little lattice that looks like this with open boundary conditions, then you might sort of wonder what to do here. Do I make a plaquette out of it or not? And you can make a kind of half plaquette if you want. Or you can always insist that you have these smooth boundary conditions like this so that the plaquette operators always work. And these guys only act on links anyway, so that doesn't matter. So you can see that this Hamiltonian is likely positive because this is minus a positive operator, and I've got a minus sign here, so that makes it positive. Yeah?
Sorry, I don't read this notation. Is it G of H or is it G multiplied with the capital H?
Okay, so the question is, what is this GH thing here? This G of H is a constant, read G subscript H. It's actually our coupling constant. H is, I don't know, there for historical reasons. G historical. And that is our microscopic model for gauge theory on a lattice in Hamiltonian picture. I'm going to make one final comment about this model, namely that it has a huge amount of symmetry. So it's meant to be a lattice gauge theory, so the local gauge group has got to be somewhere, right? So where is the local gauge group in this whole story? And the answer is the local gauge group acts on stars in this lattice. So if you look at a vertex in this lattice like this. There's 4 links involved in this star.
One question.
Yeah.
Why do you call the Hamiltonian HKG like the Cairngorm Hamiltonian, or is it?
Oh, I should call it KS, shouldn't I? Why did I call it HKG? Well, no. There's no analogy. It's really the Kogut-Susskind Hamiltonian, not the Klein-Gordon Hamiltonian. So this Hamiltonian has an extraordinarily large number of symmetries, and the symmetries act as follows. Pick a vertex in the lattice. Look at this plaquette, this star there of the 4 links that touch the vertex. And then build the following operator. So it's going to act on all 4 links. Let's label these links as E1, E2, E3, and E4. And we're going to build the following operator. Let's call it, I don't know what to call it. M again. Mu. And it's going to be right multiplied by x. Let's say x is here. On E1, right multiplied by x on E2, tensor left multiplied by x on E3, tensor left multiplied by x on E4. So So that's a unitary operator acting on a Hilbert space.
How do you choose these operator right or left?
How do I choose these operators right and left? So if the arrow comes in, I use a right multiplier, and if the arrow goes out from the vertex, I use a left multiplier. And x is an element of SU2. So this is localized at some vertex v. And it turns out, it's not hard to check from what I've told you, that mx at some vertex v commutes with my at another vertex w for all x, y, v, w. So at every vertex there's an independent copy of the action of SU2. So there's this huge number of symmetries of this Hamiltonian. Oh yeah, and obviously when I say symmetry, I mean that our Hamiltonian commutes with that symmetry. So the Hamiltonian has this gigantic number of symmetries. It's got one action of SU2 per vertex in this lattice. And that's how the local gauge symmetry manifests itself in this lattice model here. So there's not much I'm going to say anymore technically about this model. It was written down in the late 70s and did not receive so much attention because Wilson's original formulation of gauge theory on the lattice turned out to be much more useful for programs, especially involving Monte Carlo. And there are some open questions about this model. So Wilson's formulation is fairly directly, obviously, a discretization of gauge theory. This is a little bit more challenging to see if it's a discretization of proper Yang-Mills theory. Kogut and Suss can certainly argue this very persuasively by looking at the small a limit of this model and just looking at what happens to that plaquette term, turns into the curvature term in the way you might hope, and this kinetic energy term turns into the kinetic energy term in the time-like direction of the curvature term. So it's sort of, it matches what you would hope, but it hasn't received much attention. I mean, it's received some attention in the past decades, but not a huge amount. And the reason I'm telling you about this now and not Wilson's approach is that I see this as the promising candidate for the next generation of quantum simulation algorithms that will occur on quantum computers. So quantum computers don't like Monte Carlo sampling so much. It's not something that a quantum computer can do naturally, whereas a quantum computer can very naturally simulate the dynamics of local lattice models like this. They find it's much easier to write down a direct quantum algorithm that will just simulate that. Which means that when we start to build scalable quantum computers with 200, 300, 400 qubits, which may be 10 years away, we can start to imagine simulating this model very easily, whereas sampling is a pain for a quantum computer. And that will allow us to answer a whole bunch of questions that were hard for sampling but are easy for quantum computers, such as what happens, what are the unitary time dynamics of this lattice model. So this is a whirlwind introduction to Hamiltonian lattice gauge theory. There's a lot more I could say about that, but we'll leave it at that. And if you're interested, then there are certainly a handful of papers you can Google to learn more about this model. But for now, I think we'll stop. Thank you very much.